There is a point in space, perhaps many points, distributed through every galaxy in the observable universe, where the laws of physics as we understand them cease to apply, where density becomes infinite, where space-time curvature diverges without bound, where the mathematics of general relativity produces a result so extreme that the equation breaks down entirely, returning values that have no physical meaning because the physical situation they describe has no analogy anywhere else in nature. We call these singularities, and surrounding each singularity is a surface, not a physical surface, not a wall or a membrane you could touch, but a mathematical boundary beyond which the direction of time itself is redirected. Inside this boundary, every possible future path through space-time converges on the singularity. You cannot avoid it. You cannot turn around. Every trajectory, regardless of direction, regardless of speed, regardless of what you do with your engines or your body, points towards the center. Not because some force is pulling you there, but because the geometry of space-time inside the boundary has been so warped that toward the singularity is the only direction that time can flow. The future is the singularity. This boundary is the event horizon. The object defined by the singularity and its event horizon is a black hole. And there is not one type. Most people, when they think of black holes, think of a single category, the terrifying point of infinite density that devours everything that comes too close. Some people know that there are big ones and small ones. A few know that the supermassive black holes at the centers of galaxies are qualitatively different from the stellar mass black holes formed in supernovae. But the full taxonomy of black holes, the complete catalog of types, each with its own formation mechanism, its own physics, its own properties, its own behavior, and in several cases its own unresolved mysteries, is something that even many science enthusiasts have never seen laid out systematically. That is what this video is. A complete, systematic, precise account of every known and theorized type of black hole. From the stellar mass remnants of dead stars to the supermassive monsters at galactic centers. From the hypothetical microscopic black holes, predicted by certain extensions of quantum mechanics, to the primordial black holes that may have formed in the first second after the Big Bang. From the intermediate mass black holes, whose existence was disputed for decades, to the exotic theoretical variants. Charged black holes, rotating black holes, charged and rotating black holes that are described by exact mathematical solutions to Einstein's field equations, but that we have never directly observed in pure form. The taxonomy matters for a specific reason that is worth stating at the outset. Black holes are often treated as a single category of extreme object, things that are dark, massive, and absorb everything. But the differences between types of black holes are not merely differences in degree. They are differences in kind, differences in the structure of the space-time they produce, the physical processes they drive, the information they carry, and the physics they test. A supermassive black hole is not merely a large stellar mass black hole. A primordial black hole is not merely an early stellar mass black hole. A Kerr black hole is not merely a rotating Schwarzschild black hole with a quantitative modification. The rotation changes the topology of the space-time interior, introduces new physical effects like frame dragging and the Penrose process, and produces a different type of singularity. The differences in the taxonomy are the differences in the physics, and the physics is where the deepest science lives. By the end of this video, you will have a precise picture of the full black hole landscape. Not just the famous ones, but the disputed ones, the exotic ones, the ones that may have seeded the first galaxies, the ones that may constitute a fraction of the universe's dark matter, and the ones that exist only as mathematical solutions waiting for the universe to produce them in the right conditions. Let's start with what a black hole actually is, precisely, before we sort them into types. Chapter 1. What a black hole actually is. The physics before the taxonomy. Before we can meaningfully distinguish between types of black holes, we need to be precise about what defines a black hole in the first place. The popular description, a region where gravity is so strong that nothing, not even light, can escape, is directionally correct but physically imprecise in ways that matter. A black hole is a region of space-time in which the escape velocity exceeds the speed of light. But escape velocity is a Newtonian concept, and black holes are fundamentally relativistic objects. The better description is this. A black hole is a region of space-time bounded by an event horizon, inside which all future-directed causal paths lead to a singularity. The event horizon is the boundary of no return, not because anything prevents you from crossing it. You can cross it freely, without feeling anything special at the moment of crossing. But because once you have crossed it, every possible future path through space-time converges on the singularity. There is no trajectory, no matter how fast, no matter what direction. That leads back out. The event horizon is not a physical object. It is not made of anything. It is a surface defined by the causal structure of space-time, the geometry of space and time in the presence of extreme mass energy. From the perspective of an observer crossing the event horizon, nothing special happens at the moment of crossing. You feel no wall, no change in temperature, no jolt. The crossing is locally smooth. The horror of the event horizon is not in the crossing. It is in what the crossing implies about your future. Inside the horizon, the singularity is not ahead of you in space. It is ahead of you in time. It is in your future, unavoidably, the way tomorrow is in your future. The singularity itself, the point or surface at the center, is where the mathematics of general relativity breaks down. At the singularity, the density is formally infinite, the curvature of space-time is formally infinite, and the equations produce meaningless results. Most physicists believe that the singularity is not a real physical feature, but a symptom of the breakdown of general relativity at extreme scales. A signal that quantum gravity, a theory we do not yet have in complete form, is needed to describe what actually happens at the center of a black hole. The singularity may be an artifact of the approximation, not a real feature of the universe. What actually exists at the center, what replaces the singularity in a complete theory of quantum gravity, is one of the deepest open questions in physics. A black hole is completely characterized, from the outside, by only three quantities: mass, electric charge, and angular momentum, spin. This is the no-hair theorem, proved by Brandon Carter, Werner Israel, and others in the late 1960s and early 1970s. A black hole has no hair. It retains no information about what formed it, no memory of the matter, and energy that collapsed to create it. No imprint of the shape or composition of the progenitor star or the infalling gas. All of that information, from the outside perspective, is reduced to 3 numbers: mass, charge, and spin. 2 black holes with the same mass, charge, and spin are physically identical, regardless of what produced them. This no-hair theorem is the foundation of the black hole taxonomy. Because black holes are characterized by only 3 parameters, the space of possible black holes is 3-dimensional, and the taxonomy of black hole types is, essentially, a taxonomy of regions in this 3-dimensional space. Black holes with 0 charge and 0 spin, Schwarzschild black holes, occupy one corner. Black holes with spin, but 0 charge, Kerr black holes, occupy another region. Black holes with charge, but 0 spin, Reissner-Nordström black holes, occupy a third. Black holes with both charge and spin, Kerr-Newman black holes, are the most general case. And then there are the observationally defined categories: stellar mass, intermediate mass, supermassive, ultramassive, which organize black holes by mass rather than by the mathematical solution they correspond to. There is also a distinction between black holes defined by their mathematical solution type, the geometry of space-time they produce, and black holes defined by their formation mechanism and mass range. Both taxonomies are useful, and both are needed for a complete picture. We will cover both. Chapter 2. Stellar mass black holes, the most common type mass, range, approximately 3 to 100 solar masses, formation, gravitational collapse of massive stars, binary neutron star mergers, status, confirmed well-observed stellar mass black holes are the most common type of black hole in the universe. And by most common, we mean extraordinarily common. The Milky Way alone is estimated to contain between 10 million and 1 billion stellar mass black holes, the vast majority of which have never been detected because they are isolated, not accreting matter, not producing any detectable radiation, simply dark, cold, and invisible against the background of space. Stellar mass black holes form primarily through the gravitational collapse of massive stars at the end of their lives. The chain of events begins with a star of at least 20 to 25 solar masses completing its nuclear fuel cycle. A star of this mass has been sustained throughout its life by nuclear fusion in its core, first hydrogen burning, then helium burning, then carbon, neon, oxygen, and finally silicon burning, each producing a core of the next heavier element, while the fusion in the outer shells continues. Silicon burning produces iron 56, the most tightly bound of all atomic nuclei. Iron cannot be fused to produce energy. The reaction is endothermic, absorbing energy rather than releasing it. When the core of a massive star becomes iron, fusion ceases to provide pressure support. Without the outward pressure of fusion energy, gravity wins. The iron core collapses catastrophically. In less than a second, the core, which has been roughly the size of Earth, collapses to a sphere approximately 10 to 30 kilometers in diameter. The infalling material rebounds off the extraordinarily dense proto-neutron star and produces a shock wave that, if the conditions are right, propagates outward and blows off the star's outer layers in a core collapse supernova explosion. The proto-neutron star remains behind as the remnant. Whether the remnant becomes a neutron star or a black hole depends on the mass of the collapsing core and the success of the supernova shock. If the core mass exceeds approximately 2 to 2.5 solar masses, the maximum mass sustainable by neutron degeneracy pressure, called the Tolman-Oppenheimer-Volkoff limit, the core collapses further, all the way to a black hole. A neutron star cannot exist above this mass limit. The gravitational force exceeds the quantum mechanical pressure that holds neutron stars up. The collapse is total. A black hole forms. In some cases, the supernova explosion may fail entirely. The shockwave stalls, the outer layers fall back onto the proto-neutron star, and the whole star collapses silently into a black hole. This is called a failed supernova or a collapsar. Direct observational evidence for failed supernovae comes from cases where a massive star in a nearby galaxy simply disappeared from observations. No bright supernova explosion, just a star that was there and then was not. The most famous candidate is N6946-BH1, a red supergiant star in the galaxy, NGC6946, observed to brighten briefly and then disappear from view around 2009. Binary neutron star mergers are the second formation pathway for stellar mass black holes. When two neutron stars in a tight binary orbit spiral together due to the emission of gravitational waves and merge, the combined mass may exceed the Tolman-Oppenheimer-Volkoff limit, causing the merger remnant to collapse immediately to a black hole. The detection of gravitational wave event G-Bu170817 in 2017, the first detected binary neutron star merger, and its associated electromagnetic counterpart, a short gamma-ray burst and a kilonova, provided strong evidence for this formation pathway. The merger remnant in GW170817 likely collapsed to a black hole within milliseconds of the merger. Stellar mass black holes are detected primarily through two observational methods. The first is X-ray binary observations. When a stellar mass black hole is in a binary system with a companion star, it can accrete material from the companion through tidal stripping or stellar wind capture. This material forms an accretion disk, a swirling disk of hot gas orbiting the black hole that emits intense X-ray radiation as gravitational energy is converted to heat and radiation. X-ray telescopes, including ROSAT, Chandra, XMM Newton, and NuSTAR, have detected hundreds of X-ray binaries in the Milky Way and nearby galaxies, a significant fraction of which are confirmed or strongly suspected to contain black holes. The second detection method is gravitational wave observation. The LIGO and Virgo gravitational wave detectors, operational since 2015 and 2017 respectively, detect the gravitational wave signals produced when two compact objects, neutron stars or black holes, spiral together and merge. As of the most recent observing runs, LIGO and Virgo have detected well over 90 gravitational wave events, the majority of which are binary black hole mergers. These detections have not only confirmed the existence of stellar mass black holes, but have produced the first direct measurements of black hole masses across a population, revealing that stellar mass black holes exist across a mass range from approximately 3 to over 80 solar masses. The upper end of this range, black holes of 50 to 100 solar masses formed from stellar collapse, is interesting because standard stellar evolution models predict a gap in this region called the pair instability gap. In stars with cores of approximately 50 to 130 solar masses, The conditions during oxygen burning can produce electron-positron pairs in the core, reducing the thermal pressure and triggering a partial collapse, explosive oxygen burning, and a pulsational mass ejection, a pulsational pair instability supernova, rather than a standard core collapse supernova. Stars above approximately 130 solar masses trigger a complete pair instability disruption that leaves no remnant at all. This means that standard stellar evolution should not produce black holes in the mass range of approximately 50 to 130 solar masses, a predicted absence called the pair instability mass gap. Yet LIGO has detected merger events involving black holes in or near this gap, raising the question of whether these black holes formed through hierarchical mergers of smaller black holes, through binary stellar evolution pathways that avoid the pair instability limit, or through some other mechanism. Stellar mass black holes are the building blocks of the black hole hierarchy. They are the most numerous, the most studied through gravitational waves, and the type whose formation mechanisms are best understood. But they are not the most massive, not the most famous, and not the most scientifically controversial. For those distinctions, we need to go to the extremes. Chapter 3, Supermassive Black Holes. The monsters at galactic centers, mass range, millions to tens of billions of solar masses, formation, uncertain, likely multiple pathways, status, confirmed, directly imaged. At the center of virtually every large galaxy in the observable universe, and probably most galaxies above a certain mass threshold, sits a supermassive black hole. Not supermassive as a vague descriptor of something large, but as a specific technical category of object with masses ranging from about 1 million solar masses at the low end to tens of billions of solar masses at the high end. The supermassive black hole at the center of the Milky Way is called Sagittarius A star, pronounced Sagittarius A star. It has a mass of approximately 4.15 million solar masses, confirmed by decades of careful tracking of the orbits of stars in the galactic center, particularly the S stars, which orbit Sagittarius A star in highly elliptical paths at distances of a few hundred astronomical units. The star S2, also called S0-2, has an orbital period of approximately 16 years, and its orbital parameters, tracked with extraordinary precision using the ESO's gravity instrument and other facilities at the galactic center, provide the most precise measurement of Sagittarius A star's mass. Andrea Ghez and Reinhard Genzel received the Nobel Prize in Physics in 2020 for this work. Sagittarius. A star is relatively quiet by supermassive black hole standards. It is not currently accreting large amounts of material and is therefore not a bright, active galactic nucleus. It occasionally produces X-ray flares, bright eruptions lasting minutes to hours, that are thought to arise from heating of gas near the event horizon, but most of the time it is in a low accretion state. The Event Horizon Telescope collaboration released the first image of Sagittarius A star's shadow in May 2022, showing the characteristic bright ring of photons orbiting near the event horizon and the dark central shadow. The image of the photon capture cross-section of the black hole against the bright accretion flow behind it. This was the second image of a black hole's shadow by the EHT, following the 2019 image of M87 star in the galaxy Messier 87. M87 star is the other poster child of supermassive black holes. and in many ways, the more dramatic of the two. M87 star has a mass of approximately 6.5 billion solar masses, more than 1,500 times the mass of Sagittarius A star. The image of its shadow, released in April 2019, showed a bright asymmetric ring. Asymmetric because the Doppler boost from the side of the accretion disk rotating toward Earth makes that side appear brighter, with a dark central region. The ring is approximately 42 microarcseconds in angular diameter, extraordinarily small, requiring the coordinated operation of radio telescopes distributed across the Earth in an interferometric array with an effective diameter of the entire planet. Supermassive black holes in their active phase, when they are accreting large amounts of material and producing intense radiation, are what we call active galactic nuclei, AGN, which includes quasars, the most luminous subset, Seyfert galaxies, blazars, and radio galaxies. At the peak of their activity, quasars can outshine their entire host galaxy, 1 trillion stars, by factors of up to 100, with all that luminosity produced by the conversion of gravitational energy to radiation in the accretion disk and jets of the central supermassive black hole. The most luminous quasars known have luminosities exceeding 10 to the 14th solar luminosities, 100 trillion times the sun's energy output. The most massive supermassive black holes known belong to a category sometimes called ultramassive black holes exceeding approximately 10 billion solar masses. These are found in the most massive elliptical galaxies and are among the most extreme objects in the observable universe. TON 618, a quasar located approximately 10.4 billion light-years from Earth, has a central black hole with a mass estimated at approximately 66 billion solar masses. Holm 15, a star, the central black hole of the brightest galaxy in the Abell 85 galaxy cluster, has an estimated mass of approximately 40 billion solar masses, with a region of very low stellar density around it, a stellar core deficit, that is thought to be the result of the black hole's growth through binary merger, which scattered stars out of the galactic center. Phoenix A, a giant elliptical galaxy approximately 5.8 billion light-years away, may have a central black hole exceeding 100 billion solar masses, the largest yet identified, though the measurement carries significant uncertainty. How supermassive black holes form is one of the outstanding unsolved problems in astrophysics. Stellar mass black holes grow by accreting material and merging with other black holes. But the timescales required to grow a stellar mass black hole to supermassive scales through accretion alone exceed the age of the universe for the most massive examples, particularly the quasars observed at high redshift, early cosmic times, whose black hole masses already exceed billions of solar masses when the universe was less than 1 billion years old. This creates what is sometimes called the high redshift quasar problem. How did black holes of 1 billion solar masses or more exist when the universe was only a few 100 million years old? There is simply not enough time under standard accretion models to grow a stellar mass black hole to these scales. Several proposed solutions exist: direct collapse black holes, the formation of black holes with masses of 10,000 to 100,000 solar masses directly from the collapse of massive primordial gas clouds bypassing the stellar stage, could provide much heavier seeds from which supermassive black holes grow. Rapid accretion phases in which black holes accrete above the Eddington limit, the theoretical maximum accretion rate determined by radiation pressure on infalling material, could accelerate growth. Hierarchical merging of intermediate mass black holes could build up mass faster than steady accretion. The formation mechanism of the first supermassive black holes is an active area of theoretical and observational research. The James Webb Space Telescope has begun to probe this problem by observing very high redshift quasars, galaxies at cosmic dawn, and finding supermassive black holes that appear to be disproportionately large relative to their host galaxies, challenging our understanding of the co-evolution of galaxies and their central black holes. JWST data from 2023 revealed active galactic nuclei in very early galaxies that appear to contain black holes of tens of millions to hundreds of millions of solar masses, when the universe was only a few 100 million years old, putting severe pressure on standard growth models. There is an additional feature of supermassive black holes that deserves emphasis: the tight correlations between black hole mass and host galaxy properties. The M-sigma relation, first clearly established in the late 1990s, shows that the mass of a galaxy's central black hole is tightly correlated with the velocity dispersion of the galaxy's stellar bulge, the roughly spherical central component of the galaxy around the nucleus. Galaxies with faster moving stars in their bulge have more massive central black holes, with a power law relationship that holds across several orders of magnitude in black hole mass. Similar tight correlations exist between black hole mass and bulge luminosity, bulge stellar mass, and other properties. These correlations are not trivially explained. The black hole is tiny. Even a billion solar mass black hole occupies a region smaller than the entire solar system, while its host galaxy extends for tens of thousands of light years. How does the growth of the black hole know about the properties of the galaxy on scales 10 billion times larger? The answer involves feedback. The energy and radiation produced by the accreting black hole, its AGN activity, heats and disperses the gas in the surrounding galaxy, regulating star formation and modulating further black hole growth in a coupled, self-regulating system. The black hole and the galaxy grow together, each influencing the other, until a balance is reached that produces the correlations we observe. Supermassive black holes are not merely passengers in their host galaxies. They are central regulators of galactic evolution. Chapter 4: Intermediate Mass Black Holes. The missing link mass range, approximately 100 to 100,000 solar masses. Formation, uncertain, multiple proposed mechanisms. Status, evidence strong, fully confirmed examples limited. Between stellar mass black holes, up to roughly 100 solar masses, and supermassive black holes, above roughly 1 million solar masses, lies a gap, a mass range from about 100 to 100,000 solar masses that should be occupied by a class of black holes called intermediate mass black holes, or IMB-CHAKES. For decades, this mass range was the most observationally uncertain territory in black hole science. The existence of IMB-Hs was theoretically predicted and physically expected, but convincing observational evidence was elusive enough that their existence was genuinely debated among astrophysicists. The reason IMBHs are theoretically expected is straightforward. If supermassive black holes at galactic centers grew from smaller seeds, those seeds had to pass through the intermediate mass range at some point. Additionally, the hierarchical merging of stellar mass black holes, the process by which smaller black holes grow through successive mergers, should naturally produce black holes in the intermediate range over time, particularly in dense stellar environments where mergers are frequent. The most promising environments for finding IMBHs are globular clusters, dense, spherical collections of hundreds of thousands to millions of stars, gravitationally bound, typically located in the outer halos of galaxies. In the dense cores of globular clusters, stellar mass black holes can sink to the center through dynamical friction, accumulate, and potentially merge or accrete material to form an IMBH. Some globular clusters also show velocity dispersions of their central stars that are higher than expected from the visible stellar mass alone. A kinematic signature consistent with a central massive dark object. The first strong gravitational wave evidence for an IMBH came from the LIGO-Virgo detection of GW190521 in May 2019. This event was interpreted as the merger of two black holes, one of approximately 66 solar masses and one of approximately 85 solar masses, producing a remnant of approximately 142 solar masses. The smaller progenitor, at 85 solar masses, was already in the pair instability mass gap discussed in Chapter 2. The remnant, at 142 solar masses, fell clearly in the intermediate mass black hole range, making GW190521 the first confirmed detection of an intermediate mass black hole formed through a gravitational wave event. Electromagnetic evidence for IMBHs has come from several directions. Ultraluminous X-ray sources, ULXS, are X-ray point sources in nearby galaxies that are too luminous to be explained by accretion onto a stellar mass black hole at sub-Eddington rates. If their luminosity is isotropic, radiating equally in all directions, they imply black hole masses of hundreds to thousands of solar masses. Some ULXS, such as ESO 243-49HLX-1, have been proposed as strong IMBH candidates. HLX-1 has a peak X-ray luminosity of approximately 10 to the power of 42 ergs per second, at least 10 times higher than the Eddington luminosity for a stellar mass black hole, and shows behavior, including luminosity variations and spectral state transitions, characteristic of accreting black holes. Mass estimates for HLX-1 suggest a black hole of approximately 20,000 to 100,000 solar masses. The nuclei of dwarf galaxies are another hunting ground for IMBHs. If supermassive black holes scale with galaxy mass, then the smallest galaxies should host the smallest central black holes, which would fall in the intermediate mass range. The dwarf galaxy RGG 118 was found in 2015 to host a central black hole of approximately 50,000 solar masses, one of the lightest supermassive or heaviest intermediate mass black holes confirmed through dynamical measurements. NGC 4395 hosts a central black hole of approximately 10,000 to 36,000 solar masses. As surveys push to lower galaxy masses and better instrumentation enables dynamical measurements in fainter and more distant objects, the population of low-mass galactic nuclei, black holes, is growing. Despite these advances, truly convincing confirmation of IMBHs at the lower end of the mass range, a few hundred to a few thousand solar masses, in globular clusters remains elusive. The velocity dispersion measurements in globular cluster cores that suggest central dark masses have often been explainable by the collective dynamical influence of a cluster of stellar mass black holes rather than a single IMBH. Distinguishing between these scenarios requires spatial resolution that current instruments cannot provide for most globular clusters. The next generation of extremely large ground-based telescopes and future space-based gravitational wave observatories like LISA, Laser Interferometer Space Antenna, which will be sensitive to gravitational wave frequencies corresponding to mergers in the intermediate mass range, are expected to decisively resolve the IMBH question in the coming decades. Chapter 5: Primordial Black Holes. From the first second of time. Mass range, extremely wide, from subgram to thousands of solar masses or more. Formation, density fluctuations in the early universe. Status, theoretical, not yet confirmed, but not ruled out. None of the black hole types discussed so far require anything unusual about the early universe. Stellar mass black holes form from dead stars. Supermassive black holes grow from accumulated mass over cosmic time. Intermediate mass black holes sit between them, formed through mergers and dense environment dynamics. Primordial black holes are different. They are not formed from stars. They are not formed from the collapse of any stellar or galactic structure. They are formed from the collapse of density fluctuations in the primordial plasma of the very early universe, regions where, in the first fractions of a second after the Big Bang, the density was high enough that a region could collapse directly into a black hole before any structure had formed. In the early universe, the plasma was extraordinarily hot and dense, and it was not perfectly uniform. There were density fluctuations, the same fluctuations that are visible in the cosmic microwave background as temperature variations of 1 part in 100,000, spread across all scales. Most of these fluctuations were small enough that they did not collapse. Instead, they expanded with the universe, and the overdense regions eventually grew under gravity to form galaxies and galaxy clusters. But if, on some scale, the density contrast was large enough, if a region was overdense by more than about 50% relative to the background, the pressure of the plasma could not prevent gravitational collapse. A black hole would form. The mass of a primordial black hole formed in this way is determined by the size of the overdense region at the time of formation, specifically by the mass within the cosmological horizon, the causally connected region, at the time of collapse. In the very early universe, the horizon mass is tiny. In the first microsecond after the Big Bang, the horizon mass is only about a solar mass. At earlier times, the horizon mass is smaller still, a primordial black hole formed at the Planck time, the earliest moment at which the concept of a classical space-time applies, would have a mass of approximately 10 micrograms. Primordial black holes formed at the QCD phase transition, the time when quarks combined into protons and neutrons about a microsecond after the Big Bang, would have masses of approximately 1 solar mass. The mass range of primordial black holes is therefore, in principle, extraordinarily wide, from subgram masses if formed at very early times, to thousands of solar masses, if formed from large fluctuations at later times during the radiation-dominated era. This wide mass range distinguishes primordial black holes from every other type and makes their observational signatures highly varied and mass-dependent. The scientific interest in primordial black holes has surged in recent decades for a specific reason. They are a candidate for some or all of dark matter. If primordial black holes formed in sufficient numbers in the early universe, and if they have masses that have not yet been evaporated by Hawking radiation, we will discuss this shortly. They could constitute a significant fraction of the dark matter that permeates galaxies and galaxy clusters. Unlike particle dark matter candidates, such as WIMPs or axions, primordial black holes are made of ordinary matter. They are not a new type of particle, and their formation is predicted by extensions of standard cosmology that include certain types of inflationary perturbations. Primordial black holes as dark matter have been constrained by a wide variety of observations. Very low-mass primordial black holes, below about 10 to the power of 15 grams, roughly the mass of a large asteroid, would have already evaporated by Hawking radiation over the age of the universe and cannot constitute dark matter today. Primordial black holes in higher mass ranges are constrained by their gravitational lensing effects on background stars. Micro-lensing surveys such as EROS, MACO, and the optical gravitational lensing experiment have placed limits on the fraction of dark matter in compact objects at various mass ranges by their effect on the cosmic microwave background. If primordial black holes accrete material, they produce radiation that would affect the CMB spectrum and anisotropies, and by gravitational wave observations. The LIGO gravitational wave events have prompted specific consideration of whether the merging black holes could be primordial. Several of the detected events involve black holes in the mass range that could plausibly be primordial, and the merger rate inferred from LIGO observations has been compared with the predicted primordial black hole merger rate. The current observational situation is complex. Most of the mass range has been constrained. Specific mass windows have been shown to contain no more than a small fraction of dark matter. But certain mass windows remain relatively unconstrained. Most notably, the range from roughly 10 to the 17th power to 10 to the 23rd power grams, from roughly the mass of a small asteroid to the mass of the Moon, and the window around 1 to 100 solar masses where LIGO events occur. Primordial black holes in these windows could still constitute a significant fraction of dark matter, and distinguishing them from astrophysical black holes requires observational signatures beyond simply detecting mergers. One of the most striking observational proposals is that the LIGO events themselves could be primordial black hole mergers. If primordial black holes of a few to tens of solar masses exist in sufficient numbers, they would occasionally pair up through gravitational capture in the early universe and merge today, producing gravitational wave events indistinguishable in mass from stellar mass binary black hole mergers. Distinguishing primordial from astrophysical mergers in the LIGO data requires statistical analysis of the merger rate, the mass distribution, and the spin distribution of the merging black holes. Primordial black holes are expected to have low spins, while black holes formed from stellar evolution may have a broader spin distribution. Current LIGO data is consistent with both populations, and the question remains open. The Hawking radiation evaporation of very low-mass primordial black holes is also relevant. A primordial black hole of sufficiently low mass would be evaporating today at a significant rate. Black holes below approximately 10 to the 12th power kilograms, about the mass of a mountain, would have completely evaporated by now. But those near this mass are completing their evaporation in the current epoch and would produce a burst of high-energy radiation as they complete their evaporation. The detection of such bursts, characterized by a specific spectral signature predicted by Hawking's calculation, would be direct evidence for Hawking radiation and for the existence of primordial black holes. No such bursts have been detected, but the search is ongoing with gamma-ray telescopes. Chapter 6: Schwarzschild Black Holes. The simplest solution, mathematical. Type: non-rotating, uncharged. Key parameters: mass only. Status: theoretical idealization. Real black holes approximate this to varying degrees. So far, we have been categorizing black holes by their mass and formation mechanism, the observational taxonomy. Now we turn to the mathematical taxonomy. The categorization by the exact solutions to Einstein's field equations that describe different types of black holes. These mathematical solutions are distinct from each other in specific physically meaningful ways, and they correspond to different physical scenarios. The simplest black hole solution is the Schwarzschild solution, derived by Karl Schwarzschild in 1916, within months of Einstein's publication of general relativity. While Schwarzschild was serving on the Russian front in World War I, Schwarzschild found the exact solution to Einstein's field equations for the space-time geometry outside a spherically symmetric, non-rotating, uncharged mass. The resulting geometry, Schwarzschild spacetime, describes the gravitational field of any spherically symmetric mass distribution from a planet to a star to a black hole. For a black hole, the key feature of Schwarzschild spacetime is the Schwarzschild radius, the critical radius at which the event horizon forms. The Schwarzschild radius is given by r sub s equals 2 gm over c squared, where g is Newton's gravitational constant, m is the mass, and c is the speed of light. Plugging in numbers. For the Sun, the Schwarzschild radius is approximately 3 kilometers. The Sun's actual radius is about 696,000 kilometers, so the Sun is nowhere near being a black hole. But if you could compress the entire mass of the Sun into a sphere of radius 3 kilometers, it would become a Schwarzschild black hole. For Earth, the Schwarzschild radius is about 9 millimeters, the size of a small marble. For a 10 solar mass black hole, a typical stellar mass black hole, the Schwarzschild radius is about 30 kilometers. The Schwarzschild black hole is characterized by a point singularity at the center, a single point of infinite density and curvature in the classical general relativistic description, and a spherically symmetric event horizon at the Schwarzschild radius. It is the simplest possible black hole. No spin, no charge, just mass. In practice, the Schwarzschild solution is an idealization. Real black holes rotate. They inherit the angular momentum of the collapsing material that formed them, or they acquire angular momentum through accretion or mergers, and rotation is physically significant. However, many stellar mass black holes that are not actively accreting rotate slowly enough that the Schwarzschild approximation is adequate for many purposes. And the Schwarzschild solution is the foundation for understanding black hole thermodynamics. The Bekenstein-Hawking formula for black hole entropy, S equals Ka over 4 L sub p squared, where A is the event horizon area, K is Boltzmann's constant, and L sub p is the Planck length, was first derived for Schwarzschild black holes and applies, with modifications, to all types. One of the most important features of Schwarzschild spacetime is the photon sphere, a region at 1.5 times the Schwarzschild radius, or 3 gm over c squared, where photons can orbit the black hole in unstable circular orbits. The photon sphere is what creates the bright ring visible in the Event Horizon Telescope images. Photons that narrowly miss falling into the black hole orbit repeatedly before eventually escaping, accumulating the light of multiple passes around the black hole into the bright photon ring. The dark central shadow is the photon capture cross-section, the region from which photons cannot escape regardless of their direction of travel. Chapter 7. Kerr black holes. The real universe's preferred type. Mathematical type: rotating uncharged key parameters, mass and spin. Status: the most physically realistic description of astrophysical black holes. The Kerr solution, discovered by New Zealand mathematician Roy Kerr in 1963, describes the space-time geometry outside a rotating uncharged black hole. It is one of the most important exact solutions in all of physics, and arguably the most physically relevant, because every black hole that forms from a rotating progenitor, which is essentially every black hole in the universe, is, to good approximation, described by the Kerr metric. The Kerr metric introduces several features that the Schwarzschild solution lacks. The most important is the ergosphere, a region outside the event horizon, extending from the event horizon to a larger oblate surface called the ergosurface, in which space-time itself is dragged along with the rotation of the black hole. In the ergosphere, it is impossible to remain stationary. The rotation of space-time itself carries everything along with the black hole's spin, just as a whirlpool carries everything in its vicinity along with the flow. You can still escape from the ergosphere, unlike inside the event horizon. But you cannot avoid co-rotating with the black hole while you're in it. The ergosphere is the site of a theoretically proposed energy extraction mechanism called the Penrose process. In the Penrose process, an object entering the ergosphere can split into two pieces, one with positive energy that escapes to infinity, and one with negative energy, in the sense of the killing energy, a conserved quantity in Kerr spacetime, that falls into the black hole. The net result is that the escaping piece has more energy than the original object. Energy has been extracted from the rotation of the black hole. The rotational kinetic energy of the black hole is reduced. The black hole slows. A maximally spinning Kerr black hole could in principle yield up to 29% of its total mass energy through the Penrose process. The astrophysical importance of the Penrose process, or more precisely, its generalization to electromagnetic fields, the Blandford-Znajek mechanism, cannot be overstated. The relativistic jets produced by active galactic nuclei and some X-ray binaries, collimated beams of plasma and radiation extending hundreds of thousands of light years, from galactic centers, are thought to be powered by the extraction of rotational energy from a spinning black hole through its interaction with the surrounding magnetic field. The Blandford-Znajek mechanism converts the spin energy of the black hole into the kinetic energy of the jet, powering some of the most energetic continuous phenomena in the universe. Without rotating Kerr black holes, there would be no relativistic jets. Without relativistic jets, the evolution of galaxies over cosmic time would be fundamentally different. Kerr black holes also have a ring singularity rather than a point singularity. Instead of the infinite density point at the center of a Schwarzschild black hole, the Kerr black hole has a ring of infinite density in the equatorial plane. One-dimensional singularity that extends around the rotation axis. The ring singularity introduces a remarkable mathematical feature. In principle, in the mathematical solution, not necessarily in physical reality, there is a pathway through the center of the ring that avoids the singularity and connects to another region of space-time, a hypothetical other universe, or another region of our own universe. This is the Kerr wormhole, and while it exists as a feature of the mathematical solution, most physicists do not believe it corresponds to a physical reality that any observer could survive to traverse, because the interior of a rotating black hole contains unstable regions where the smallest perturbation would cause a catastrophic restructuring of the geometry. The spin of a Kerr black hole is parameterized by the dimensionless spin parameter a star equals J over M, in natural units where G equals C equals 1, which ranges from 0, Schwarzschild limit, no spin, to 1, extremal Kerr, maximum possible spin. For a star equals 1, the event horizon and the ergosphere meet at the equator, and the singularity is exposed. The black hole becomes a naked singularity, which most physicists believe is prevented by the cosmic censorship conjecture. Real astrophysical black holes likely have spin parameters ranging from near 0 to near the maximum, depending on their formation history and accretion. Measurements of black hole spin are one of the active frontiers in observational astrophysics. Spin can be measured through the analysis of X-ray reflection spectra. The distortion of the iron K-alpha emission line produced in the accretion disk by the extreme Doppler shifts and gravitational redshifts near a spinning black hole. Spin can also be estimated from the quasi-periodic oscillations observed in X-ray emission from accreting black holes. Both methods have significant systematic uncertainties, but several stellar mass black holes and X-ray binaries have been measured to have spin parameters near the maximum. Cygnus X1, one of the first black hole candidates identified, has a spin parameter measured at approximately 0.98, very close to the maximum. The spin of a black hole is also directly connected to the innermost stable circular orbit, the ISCO, the smallest radius at which material can orbit the black hole stably. For a non-rotating Schwarzschild black hole, the ISCO sits at 3 times the Schwarzschild radius. For a maximally spinning Kerr black hole, where the orbital motion is co-rotating with the spin, the ISCO can approach the event horizon itself, down to approximately 0.5 Schwarzschild radii for maximum prograde spin. This matters enormously for the efficiency of energy extraction through accretion. The further in the accretion disk extends towards the event horizon, the more gravitational potential energy is released as heat and radiation before the material crosses the horizon. A maximally spinning Kerr black hole can convert up to approximately 42% of the infalling mass energy into radiation through accretion, compared to about 6% for a non-rotating Schwarzschild black hole. This factor of 7 difference in radiative efficiency is the reason that rapidly spinning black holes are associated with the most luminous AGN and the most powerful jets. Spin is not merely a descriptive property of a black hole. It is the engine of some of the most energetic phenomena in the observable universe. Chapter 8: Reissner-Nordström. Black holes. Charged and still mathematical type. Non-rotating, electrically charged key parameters. Mass and electric charge. Status. Exact solution. Physically realized charge is likely negligible in nature. The Reissner-Nordström solution, derived independently by Hans Reissner in 1916 and Gunnar Nordström in 1918, describes the space-time geometry outside a spherically symmetric, non-rotating black hole that carries a net electric charge. It is the direct generalization of the Schwarzschild solution to include charge in the same way that the Kerr solution generalizes Schwarzschild to include spin. The Reissner-Nordström solution introduces a fundamentally different horizon structure compared to Schwarzschild. A Schwarzschild black hole has a single event horizon. A Reissner-Nordström black hole, depending on the relationship between its mass and charge, can have 2 horizons: an outer event horizon and an inner Cauchy horizon. The outer event horizon is the black hole's boundary of no return, the surface beyond which you cannot escape. The inner Cauchy horizon is a second surface deeper inside the black hole, where the nature of space-time changes dramatically. The region between the 2 horizons has a peculiar structure in which the singularity is not space-like, unavoidably in your future, as in the Schwarzschild case, but time-like, meaning it extends along the time direction, and in principle you could avoid it by steering around it spatially, rather than being inevitably swept into it. At a specific relationship between mass and charge, when the charge parameter equals the mass in natural units, Q equals m in geometric units, where G equals C equals 1, the 2 horizons merge into a single degenerate horizon. This is the extremal Reissner-Nordström black hole. The extremal case has several extraordinary properties. Its surface gravity, the analog of the gravitational pull at the event horizon, is 0. By the Hawking temperature formula, T equals h bar times kappa over 2 pi k sub b, where kappa is the surface gravity, a 0 surface gravity corresponds to 0 Hawking temperature. An extremal Reissner-Nordström black hole does not radiate. It is a cold black hole, thermodynamically stable against evaporation, that could, in principle, persist indefinitely without losing mass to Hawking radiation. If the charge exceeds the mass in geometric units, Q greater than m, the 2 horizons disappear entirely and the singularity becomes naked, exposed to the external universe without an event horizon surrounding it. This is a naked singularity, which most physicists believe is physically forbidden by Roger Penrose's cosmic censorship conjecture. The conjecture that the laws of physics forbid the formation of naked singularities from physically reasonable initial conditions. The charged black hole solution saturates this conjecture at the extremal limit. the maximum charge a black hole of given mass can carry without violating cosmic censorship is exactly Q equals m. Why does charge matter for black hole physics if astrophysical black holes are not expected to carry significant net charge? The answer is that the mathematical structure of the Reissner-Nordström solution, particularly the Cauchy horizon, the extremal limit, and the naked singularity threshold, is physically instructive, even if the solution is not directly realized in nature. Many of the key features that appear in the Reissner-Nordström case, including the Cauchy horizon, instability. The inner horizon is thought to be unstable to perturbations, meaning that any real infalling matter or radiation would cause it to collapse. Reappear in the Kerr solution for rotating black holes, where the Cauchy horizon plays an important role in debates about the interior structure of real astrophysical black holes. Understanding the charged case provides crucial physical intuition for the rotating case. Real astrophysical black holes are expected to carry negligible net electric charge. Any initial charge would be rapidly neutralized by the preferential accretion of oppositely charged particles from the surrounding plasma. A black hole with a net positive charge selectively attracts electrons more strongly than protons, and vice versa, until the charge is neutralized. The time scale for charge neutralization is extremely short. So the Reissner-Nordström solution, while exact and mathematically well-defined, is generally considered a theoretical idealization, rather than a description of any real black hole in the universe. The Cauchy horizon instability is worth discussing in more detail because it has important implications for the predictability of physics inside black holes. The Cauchy horizon, the inner horizon of the Reissner-Nordström solution, is technically a surface beyond which classical determinism fails. The Einstein field equations admit multiple possible continuations beyond the Cauchy horizon, meaning the future of an observer who crosses it is not uniquely determined by the past initial data. This is the strong cosmic censorship problem. The question of whether nature prevents observers from ever reaching such surfaces. Roger Penrose's strong cosmic censorship conjecture states that Cauchy horizons in realistic physical spacetimes are always unstable, collapsing into a curvature singularity when any perturbation is present, thereby preventing observers from reaching the surface at which determinism fails. The instability of the Cauchy horizon in the Reissner-Nordström case, and by extension in the Kerr case, where a similar inner horizon exists, is a concrete realization of the conjecture. Any infalling radiation from the exterior is infinitely blue-shifted at the Cauchy horizon, concentrating infinite energy density there and triggering a singularity that destroys the horizon before any observer can cross it. Nature, in this sense, enforces its own predictability by eliminating the surface at which it would fail. Whether this enforcement is exact, or whether some residual structure survives at the quantum level, is an open question connected to the information paradox. There is one important exception worth noting. In string theory and certain other extensions of standard physics, black holes can carry charges associated with generalized gauge symmetries that are not electromagnetic. Charges under higher dimensional gauge fields that do not have the same easy neutralization mechanism as electric charge. These are sometimes called black holes with hair, which may seem to contradict the no-hair theorem, but they are charges associated with long-range fields that can be measured from outside the horizon, satisfying the theorem's requirements. The study of charged black holes in extended theories of gravity is an active area at the frontier of theoretical physics, particularly in the context of the holographic correspondence, ADS/CFT, where charged black holes in anti-d Sitter space correspond to finite-density quantum field theory states. Chapter 9. Kerr-Newman black holes, the most general classical black hole. Mathematical type, rotating and electrically charged key parameters: mass, spin, and electric charge. Status, the most general exact solution, astrophysically realized without significant charge. The Kerr-Newman solution, derived by Ezra Newman and collaborators in 1965, is the most general black hole solution in classical general relativity, combined with classical electromagnetism. It describes a rotating electrically charged black hole, the combination of the Kerr rotation and the Reissner-Nordström charge into a single solution. By the no-hair theorem, the Kerr-Newman metric is the complete description of all possible black holes in classical general relativity plus electromagnetism. Every possible black hole is described by some values of mass m, spin j, and charge q in the Kerr-Newman framework. The Kerr-Newman solution is the culmination of what is sometimes called the golden age of black hole theory, the period from roughly 1963 to 1975, during which the mathematical structure of black holes was systematically worked out. The solution inherits all the features of both Kerr and Reissner-Nordström: the ergosphere and frame dragging from Kerr, the two-horizon structure and extremal limit from Reissner-Nordström, the ring singularity from Kerr. The combined effect of charge and rotation produces a particularly rich structure of regions with different causal properties inside the event horizon. The extremal Kerr-Newman black hole, the configuration that maximizes the combination of spin and charge relative to mass, such that the outer and inner horizons merge, is of special interest in theoretical physics because of its connection to supersymmetry. Extremal black holes in string theory and supergravity saturate a bound called the BPS bound, after Bogomolny, Prasad, and Sommerfeld, and they preserve a fraction of the supersymmetry of the background theory. This makes them exactly calculable in ways that non-extremal black holes are not. The microscopic derivation of black hole entropy, counting the quantum states that produce the macroscopic Bekenstein-Hawking entropy, was first achieved for extremal charged black holes in string theory by Andrew Strominger and Kumran Vafa in 1996, in one of the most important results in the history of quantum gravity. The Strominger-Vafa calculation showed for the first time that the entropy of a specific type of extremal charged black hole could be reproduced by counting microscopic string theory states, providing a concrete realization of the idea that black hole entropy has a statistical origin. As with the Reissner-Nordström case, astrophysical Kerr-Newman black holes with significant net charge are not expected. The real universe's black holes are well described by the Kerr metric, rotating but uncharged. The Kerr-Newman solution is primarily a mathematical and theoretical tool, but it is the theoretical foundation that underlies our understanding of black hole thermodynamics, the information paradox, and quantum gravity. Chapter 10. Micro black holes. At the quantum frontier mass range, below approximately 10 to the power of -5 grams, the Planck mass, to potentially stellar mass formation, hypothetical, not yet observed. Status: theoretical prediction of certain quantum gravity and extra dimension models. Every black hole type we have discussed so far exists within the framework of classical or semi-classical general relativity. General relativity with quantum field theory effects, like Hawking radiation, added as a correction. None of them require a complete theory of quantum gravity. Micro black holes, by contrast, are objects whose existence and properties lie precisely at the boundary between general relativity and quantum mechanics. Objects so small that quantum gravitational effects dominate their physics, and where a complete theory of quantum gravity would be required to describe them fully. In standard four-dimensional general relativity, there is a natural minimum size for a black hole. The Planck length, approximately 1.6 times 10 to the power of -35 meters. A black hole whose Schwarzschild radius equals the Planck length has the Planck mass, approximately 2.2 times 10 to the power of -8 kilograms, or about 22 micrograms. This is the scale at which quantum corrections to general relativity become of order unity, where quantum gravity is not a small perturbation, but the dominant physics. A black hole of Planck mass is simultaneously a quantum object and a gravitational object, and no current theory can fully describe it. In standard four-dimensional physics, micro black holes of Planck mass or below are not expected to form under any physical conditions in the present universe. The densities required are far beyond anything achievable by any known process. But certain extensions of physics change this picture dramatically. The most widely discussed proposal involves extra spatial dimensions. In scenarios where the universe has more than the 3 spatial dimensions we observe, with the extra dimensions compactified, curled up to a small size, gravity can spread into the extra dimensions at short distances, making it stronger than standard 4-dimensional gravity at those scales. The effective Planck scale in such theories, the energy scale at which gravity becomes strong and quantum gravitational effects become important, can be much lower than the standard 4-dimensional Planck scale. In some models with large extra dimensions, proposed by Arkani Hamed, Dimopoulos, and Diwali in 1998, the ADD model, the effective Planck scale could be as low as a TeV, a tera-electron volt, the energy scale of the Large Hadron Collider. In such theories, particle collisions at TeV energies could produce micro black holes, tiny, extremely hot black holes that would immediately evaporate through Hawking radiation in an extremely brief burst. This prediction was taken seriously enough that before the LHC turned on at full energy in 2010, there was public concern that the LHC might produce black holes that could swallow the Earth. This concern was thoroughly addressed by detailed theoretical analyses, which showed that even if micro black holes were produced, they would be of negligible mass and would evaporate almost instantaneously through Hawking radiation. No black hole produced at the LHC could grow or persist. Furthermore, the Earth is continuously bombarded by cosmic ray particles at energies far exceeding the LHC's, and has survived this bombardment for billions of years, providing empirical evidence that TeV scale particle collisions do not produce dangerous black holes. No micro black holes were detected at the LHC. This non-detection has placed strong constraints on certain extra-dimension models, ruling out the simplest ADD scenarios where micro-black holes would have been produced at LHC energies. More complex models with different extra-dimension geometries remain viable. The search for signatures of micro-black hole production, specifically the characteristic democratic pattern of Hawking radiation in which the black hole evaporates into all particle species with equal probability, continues in LHC data analysis and is one of the motivations for proposed higher energy collider projects. What would a micro-black hole production event actually look like in an LHC detector? If produced, a micro-black hole of, say, a few TeV of mass would exist for approximately 10 to the power of minus 26 seconds before evaporating through Hawking radiation. Its Hawking temperature would be enormous. The temperature is inversely proportional to mass. And a Planck scale black hole has a Hawking temperature comparable to the Planck temperature, roughly 10 to the power of 32 Kelvin. At this temperature, the black hole would emit all known particle species with equal probability: quarks, leptons, gauge bosons, Higgs bosons, photons, gravitons, in a roughly equal multiplicity, high-energy burst. The decay would produce dozens to hundreds of high-energy particles in a near-spherically symmetric explosion, unlike the strongly forward-peaked collimated jets produced by the standard QCD processes that dominate LHC events. This spherical, democratic, high-multiplicity signature is the defining characteristic that physicists searched for in LHC data. It was not seen. The failure to detect it, combined with the increasingly precise measurements of standard model processes, has pushed the effective Planck scale in extra-dimension scenarios to higher energies, where micro-black hole production at the current LHC is kinematically forbidden. Even if micro-black holes are never produced artificially, they may have been produced in the early universe at high energies during inflation or immediately after reheating. The primordial black holes discussed in Chapter 5 overlap with micro-black holes at the low mass end of their distribution. Primordial black holes formed at very early times, when the horizon mass was extremely small, would be micro-black holes by any definition, and they would have evaporated long ago through Hawking radiation. The signatures of these evaporations, bursts of radiation at specific energies, could in principle be detected in cosmological backgrounds. There is also a remarkable connection between micro-black holes and the information paradox. If a micro-black hole evaporates completely through Hawking radiation, the question of what happens to the information that went into making it becomes acute. The information paradox, which we will discuss in more detail in Chapter 14, is most sharply posed for micro-black holes, precisely because they can evaporate completely, leaving apparently nothing behind except thermal radiation that carries no information about the initial state. Whether micro-black holes leave behind a stable remnant or evaporate completely with information encoded in subtle correlations of the radiation, or evaporate completely destroying information. 3 scenarios with very different implications for fundamental physics is one of the deepest open questions in theoretical physics. Chapter 11: White Holes. The time-reversed black hole. Mathematical type: the time reverse of a black hole. Key parameters: same as black holes: mass, spin, charge, status, exact solution, almost certainly not physically realized in our universe. Every mathematical solution to Einstein's field equations has a time reverse, a solution with the same geometry, but with the direction of time flipped. The time reverse of a black hole is a white hole, where a black hole is a region of space-time into which things can fall, but from which nothing can escape. A white hole is a region from which things can escape, but into which nothing can fall. A black hole absorbs. A white hole expels. The white hole is not a separate type of object from a black hole. It is part of the complete, maximally extended spacetime that includes the black hole. The Kruskal-Sekaris coordinates, developed in the 1960s as the maximally extended description of Schwarzschild spacetime, reveal that the full mathematical solution of a black hole actually contains 4 regions: the exterior region, our universe; the black hole interior, the region inside the event horizon from which nothing can escape; a white hole interior, a region from which matter and light are expelled, but into which nothing can fall; and a second exterior region, a separate universe, sometimes called the Einstein-Rosen bridge or wormhole, connected to ours through the black hole interior. The white hole region in the Kruskal-Sekaris diagram is the time reverse of the black hole. It is bounded by a past event horizon, a surface from which things can only exit, the time reverse of the future event horizon of a black hole from which nothing can exit. Matter and light in the white hole interior can only move outward, away from the singularity and through the past event horizon into the exterior region. Nothing can enter the white hole from outside. The physical status of white holes is almost universally regarded as that of a mathematical fiction rather than a physical reality. For several reasons. First, real astrophysical black holes do not form from the maximally extended Schwarzschild spacetime. They form from collapsing matter. The Kruskal spacetime is the vacuum solution in the absence of any matter, and the collapsing star solution that actually describes a physically formed black hole does not contain a white hole region. The white hole is a feature of the mathematical extension of the vacuum solution, not a feature of physical black holes. Second, even in the maximally extended solution, the white hole is unstable. The white hole's past singularity is unstable to perturbations. The slightest infalling material or radiation causes the white hole to collapse and become a black hole. Third, there is a thermodynamic objection. A white hole would be an extraordinarily low entropy object that spontaneously ejects material, violating the tendency of entropy to increase. It would be the cosmological equivalent of a shattered glass spontaneously reassembling. Despite these objections, white holes have attracted renewed theoretical attention in a specific context: the endpoint of black hole evaporation. If a black hole evaporates completely through Hawking radiation over an incomprehensibly long timescale, the question of what replaces it, what space-time looks like after the black hole has gone, is the subject of active theoretical work. One proposal, developed by Carlo Rovelli and Francesca Vidotto and others in the context of loop quantum gravity, is that when a black hole evaporates to Planck mass, quantum gravitational effects prevent further evaporation, and the black hole bounces into a white hole, a brief explosion of the remaining material, time reversed, that expels everything in a burst before the spacetime returns to flat. The timescale for this bounce in the external universe would be astronomical, set by the black hole's evaporation time. So these white hole bounces would not be occurring today for stellar mass or supermassive black holes. But they might be occurring for the smallest primordial black holes whose evaporation times are shorter. The observational signatures of white hole bounces, a specific spectral pattern in the emission, are a topic of current theoretical and observational discussion, though no detection has been made. Chapter 12. Hawking, Radiation, and Black Hole. Remnants. What evaporation leaves behind. The thermal radiation emitted by black holes through Hawking radiation is not merely a slow loss of mass. It raises one of the deepest conceptual questions about the nature of black holes. When a black hole evaporates completely, what happens to the information that went into making it? As described in Chapter 10 in the context of micro-black holes, the information paradox concerns the apparent loss of quantum information during black hole evaporation. The argument, in its most direct form, is this: quantum mechanics requires that the evolution of any physical system be unitary. Information is never destroyed, only redistributed. If you know the exact quantum state of a system at one time, you can, in principle, reconstruct the exact quantum state at any other time. This is a foundational principle of quantum mechanics. But Hawking's original calculation showed that the radiation emitted by an evaporating black hole is exactly thermal. It carries no information about what fell into the black hole, just as the thermal radiation from a warm body carries no information about the specific atoms that generated it. If the radiation is thermal and carries no information, and if the black hole eventually evaporates completely, then the information about everything that fell into the black hole is gone, destroyed. This would violate unitarity, one of the bedrock principles of quantum mechanics. This is the information paradox, and it has been one of the central problems in theoretical physics for nearly 50 years. The possible resolutions define a specific taxonomy of subtypes or endpoint states for evaporating black holes. The first resolution is that information is encoded in the Hawking radiation in subtle quantum correlations between early and late emitted photons. Correlations that are present but invisible in Hawking's thermal approximation. In this view, the radiation is not exactly thermal. It is approximately thermal to very high precision, but the exact quantum state of the radiation is not a thermal state, but a pure state with complex correlations that carry all the information about the initial black hole. The radiation looks thermal because the correlations are extraordinarily complex and practically undetectable. But in principle, they are there. This is the view taken by most mainstream physicists today, motivated by the insights of the ADS/CFT correspondence, which demonstrates that black hole formation and evaporation in anti-de Sitter space is dual to a unitary quantum field theory on the boundary. Information is preserved, just scrambled into extremely complex radiation correlations. The black hole in this view leaves no remnant. It evaporates completely, and information is in the radiation. A major theoretical advance came in 2019 through 2020, when several groups, including Ahmed Almhairi, Nita Engelhardt, Henry Maxfield, and Jeff Pennington, derived the Page curve for an evaporating black hole using a combination of semi-classical gravity, the island formula, and replica wormholes. The page curve is the expected behavior of the entanglement entropy of the radiation if information is preserved. The entropy of the radiation should increase early in the evaporation, as the black hole loses mass, reach a maximum at approximately the halfway point, the page time, and then decrease as the remaining radiation becomes increasingly correlated with the early radiation, eventually returning to zero when the black hole has completely evaporated. Hawking's original calculation produces a radiation entropy that monotonically increases throughout evaporation, a page curve that never turns over, contradicting unitarity. The new calculation using the island formula reproduces the correct page curve, including the turnover, by including the contribution of so-called islands, regions inside the black hole that contribute to the entropy calculation in a specific quantum gravitational manner. This was widely regarded as a major breakthrough in the information paradox, though the physical interpretation of the islands and the precise mechanism by which information is extracted remain areas of active research. The information paradox is not solved, but the tools to address it have become substantially more sophisticated. The second resolution is the remnant hypothesis. The black hole evaporates down to a stable or metastable Planck scale remnant, an object of Planck mass and Planck size, that contains all the information that fell in, locked within a Planck scale configuration that quantum gravity stabilizes against further evaporation. The information never escapes the remnant. It is preserved inside it indefinitely. This proposal has the attraction of not requiring any modification to quantum mechanics or unitarity, but it faces severe difficulties. The remnant would have to carry an enormous amount of information in a Planck scale object, implying an infinite degeneracy of remnant states that leads to other theoretical difficulties. The remnant hypothesis is less favored than the information in the radiation view, but has not been definitively ruled out. The third resolution, information destruction, holds that the information paradox represents a genuine violation of quantum mechanical unitarity, and that the correct description of black hole evaporation requires modifying quantum mechanics. This was Hawking's original position, which he maintained for many years before eventually conceding in a famous 2004 conference presentation that he believed information was preserved after all. Information destruction is the least favored of the three views, but it has not been definitively disproved, and the question of whether quantum mechanics must be modified at the Planck scale remains open. One specific and dramatic proposal for how information escapes is the firewall hypothesis, put forward by Ahmed Almheri, Donald Marolf, Joseph Polchinski, and James Sully in 2012. They argued that maintaining unitarity and preserving the equivalence principle, which says that an observer crossing the event horizon should not experience anything special at the moment of crossing, simultaneously leads to a contradiction. The resolution they proposed is that the interior of the black hole is actually replaced by a firewall, a region of intense radiation at the event horizon that would incinerate any infalling observer. An observer crossing the event horizon would not experience smooth, empty space. They would be immediately destroyed by the firewall. This proposal generated enormous debate in the theoretical physics community, and while it has not been definitively resolved, it has sharpened the understanding of the constraints that any complete theory of quantum gravity must satisfy. Chapter 13: Regular Black Holes. Singularity-free solutions. Mathematical type: black holes with non-singular centers. Key parameters: varies by model status, theoretical, motivated by quantum gravity. All the black hole solutions discussed in the mathematical taxonomy, Schwarzschild, Kerr, Reissner-Nordström, Kerr-Newman, contain singularities. The singularities are points or regions of infinite curvature and density where the classical equations break down. Most physicists view the singularity as a symptom of the incompleteness of classical general relativity, a signal that quantum gravitational effects, which general relativity ignores, become dominant at extreme curvatures and resolve the singularity into something finite and physical. Regular black holes are black hole solutions that have all the external properties of standard black holes: event horizons, photon spheres, accretion disks, gravitational wave emission. But that replaced the central singularity with a non-singular core. The first regular black hole solution was proposed by James Bardeen in 1968, known as the Bardeen black hole. It is a spherically symmetric black hole with a de Sitter, constant positive curvature, core at the center instead of a singularity. The density at the center is finite and large, but not infinite. The Bardeen solution satisfies the Einstein field equations with a specific form of nonlinear electrodynamics as the source, though the physical interpretation of this source in terms of realistic matter is not entirely straightforward. Regular black holes have attracted significant attention as possible descriptions of what quantum gravity actually produces at the center of black holes. In loop quantum gravity, for example, the quantization of space-time at the Planck scale provides a minimum length. Space-time cannot be compressed below the Planck scale, which naturally cuts off the infinite density of the classical singularity. Loop quantum black holes, studied by Abhay Ashtekar, Javier Olmedo, and Parampreet Singh, among others, replace the Schwarzschild singularity with a high-density but finite quantum bounce region, creating a regular spacetime. In string-inspired models, the hard singularity is replaced by a region of string-scale curvature where the classical description breaks down, but the physics remains well-defined. Regular black holes generally have the same external observational appearance as singular black holes: the same shadow, the same gravitational wave emission, the same accretion disk dynamics. The differences are hidden inside the event horizon, where no external observer can directly probe them. However, regular black holes can differ from singular ones in two observationally relevant ways. First, their Hawking temperature and entropy can differ from standard black holes of the same mass, particularly in the final stages of evaporation when the radius approaches the Planck length. Second, the resolution of the singularity can change the fate of infalling matter and the information content of the Hawking radiation, potentially providing a resolution to the information paradox. The question of whether any regular black hole model is actually correct, whether the singularity is resolved by nature, is answerable only by a complete and tested theory of quantum gravity. We do not yet have such a theory, but the study of regular black hole solutions provides a framework for exploring what quantum gravity might imply for the physics of black hole interiors, and several current research programs are aimed at connecting regular black hole models to predictions that can be tested through gravitational wave observations, black hole shadow observations, or other means. Chapter 14. Exotic alternatives, fuzzballs, gravastars, and black hole mimickers. Mathematical type, alternatives to classical black holes. Status, theoretical. Not observationally confirmed, but not ruled out. The event horizon. Telescope images of Sagittarius. A star and M87 star are direct evidence that the objects at the centers of these galaxies are extremely compact, and that their light ring structure matches the predictions of general relativity for black holes. But these images, while consistent with black holes, do not definitively prove that the objects have event horizons in the strict classical sense, because distinguishing an event horizon from a very compact object that merely mimics a black hole's external appearance requires observations that probe physics at or inside the photon sphere. This opens the door, theoretically, to objects that are not black holes in the classical sense, but that produce observational signatures nearly identical to classical black holes. These are collectively called black hole mimickers, and several specific proposals exist. Fuzzballs are a string theory concept. In string theory, the information paradox is resolved by the proposal that what we call a black hole is actually a fuzzball, a highly excited state of fundamental strings and branes that occupies the volume that would be the black hole's interior, with no event horizon and no singularity in the traditional sense. The fuzzball's surface is not a sharp mathematical surface like an event horizon. It is a quantum fuzz of string excitations, stretched and vibrating at the string scale. From far outside, a fuzzball is essentially indistinguishable from a classical black hole. It has the same mass, the same gravitational field, the same deflection of light, the same photon ring. But it has no interior in the general relativistic sense. What looks like a black hole from outside is actually a compact quantum object whose interior is filled with the fizzle of stringy degrees of freedom rather than the smooth space-time of general relativity. The fuzzball proposal, developed primarily by Samir Mathur and collaborators beginning in the early 2000s, offers a radical resolution to the information paradox. There is no information paradox because there is no event horizon, no interior, no Hawking radiation in the strict sense. The thermal appearance of Hawking radiation arises from the quantum thermal emission of the fuzzball surface, which is not exactly thermal but carries information. Every classical black hole is a fuzzball. They are one and the same, the classical description being an approximation to the quantum reality. The observational differences between fuzzballs and classical black holes are extremely subtle. Echoes, repeated gravitational wave signals arriving after the main merger signal, caused by partial reflection of gravitational waves at the fuzzball surface, rather than the complete absorption at a classical event horizon, are one proposed signature. Several analyses of LIGO and Virgo data have searched for post-merger echoes, with tentative claimed detections that have not been confirmed and have been disputed. The sensitivity of current detectors may be insufficient to definitively detect or rule out echoes at the expected amplitude. Future gravitational wave detectors with higher sensitivity may be able to resolve this question. Gravastars, gravitational vacuum condensate stars, proposed by Powell Mazur and Emil Motola in 2001, are another black hole mimicker. A gravastar consists of a de Sitter core, a region of positive vacuum energy, surrounded by a thin shell of ultra-dense matter, with the external spacetime described by the Schwarzschild metric. The de Sitter core has negative pressure that supports the object against gravitational collapse. A gravastar has no event horizon and no singularity. From outside, it looks identical to a Schwarzschild black hole. The surface of the gravastar sits just outside where the event horizon would be for a black hole of the same mass. Anisotropic stars, boson stars, hypothetical objects made of bosonic particles in a quantum coherent state, fermion boson stars, and dark matter stars are additional exotic compact objects that can, under certain conditions, reach densities high enough to produce gravitational lensing and photon rings similar to black holes. These objects are studied as theoretical alternatives to classical black holes, but none have been observationally confirmed, and all face significant formation and stability challenges. The key observational signatures that could distinguish these exotic objects from classical black holes include gravitational wave echoes, the reflection signature at the surface rather than complete absorption, tidal deformability measurements in binary mergers. Different equations of state produce different deformations during in spiral, and electromagnetic emission from the surface if in falling. Material lands on a surface rather than crossing an event horizon, which would produce a different X-ray spectral signature than a black hole with an event horizon. Current data is consistent with classical black holes and does not require exotic alternatives, but the precision required to definitively rule out all exotic alternatives has not yet been achieved. Chapter 15. The direct collapse. Black hole, the most massive seeds. Mass range, 10,000 to 100,000 solar masses at formation. Formation, direct collapse of primordial gas clouds in the early universe. Status, theoretical, not yet confirmed, but increasingly supported by JWST observations. We discussed the high redshift quasar problem in Chapter 3, the question of how supermassive black holes of billions of solar masses existed when the universe was less than 1 billion years old. The direct collapse black hole DCBH scenario is the most widely discussed solution to this problem, and it deserves its own chapter because it represents a fundamentally different formation pathway from all others discussed. In the standard picture, black holes form from stars. A star forms, burns its fuel, exhausts it, and collapses, leaving behind a stellar remnant that may be a neutron star or a black hole. This requires the gas to fragment into stars first. But under specific conditions in the early universe, gas clouds could potentially collapse directly into a black hole without ever fragmenting into stars. The conditions require that the gas be hot enough that the gene's instability, the instability that normally breaks a large gas cloud into smaller fragments that become stars, is suppressed. If the gas is kept warm, above about 10,000 Kelvin, by an intense UV radiation field from nearby star-forming galaxies, the molecular hydrogen that normally cools the gas is photodissociated, destroyed, preventing efficient cooling and fragmentation. The gas cloud, unable to fragment, collapses as a single, monolithic object, forming either a supermassive star of 10,000 to 100,000 solar masses that rapidly collapses to a black hole, or directly a black hole of the same mass range through direct catastrophic collapse. The resulting DCBH has a mass of 10,000 to 100,000 solar masses at formation, already in the intermediate mass range, with a far shorter path to supermassive scales than a stellar mass seed. Starting from 100,000 solar masses and accreting at the Eddington rate, a black hole could reach 1 billion solar masses in roughly 500 million years, much more consistent with the observed high redshift quasars than a stellar mass seed. The James Webb Space Telescope has begun to reveal objects that may be DCBH candidates. In 2023, analysis of JWST spectroscopic data identified a compact, high redshift galaxy, GN-ZO 11, with properties that some researchers interpret as a rapidly accreting black hole of approximately 2 million solar masses when the universe was approximately 430 million years old. An object that, given its extreme compactness and high accretion rate, is difficult to explain without a massive black hole seed. Other JWST objects, including the so-called little red dots, compact red sources at high redshift with broad emission lines consistent with AGN activity, are being interpreted as the direct collapse and early growth phase of what will become supermassive black holes. The DCBH scenario is currently the leading explanation for these objects, though alternative interpretations, including very dense and rapidly star-forming galaxies, have not been definitively excluded. Direct collapse black holes represent a third fundamental formation category for black holes, alongside stellar collapse and primordial formation. And they are specifically predicted by the physics of the early universe under conditions that are well motivated by galaxy formation theory. Their observational confirmation with JWST would resolve the high redshift quasar problem and establish the direct collapse pathway as the origin of the universe's most massive black holes. Chapter 16: Ultramassive Black Holes Beyond the Billion Solar Mass Threshold. Mass range above approximately 10 billion solar masses. Formation, long-term accretion, and galaxy mergers. Status: confirmed. A handful of examples known. We touched on ultramassive black holes briefly in Chapter 3, but they deserve more systematic treatment because they represent not just the extreme end of the supermassive range, but potentially a physically distinct regime where the standard growth mechanisms are pushed to their limits, and the relationship between the black hole and its host galaxy takes on extreme characteristics. The transition from supermassive to ultramassive is not sharply defined in the literature. Most sources use roughly 10 billion solar masses as the threshold. But the distinction matters because the very largest black holes present specific physical puzzles. The Eddington luminosity, the maximum luminosity at which a black hole can accrete before radiation pressure, prevents further infall, scales linearly with mass. A 10 billion solar mass black hole has an Eddington luminosity of approximately 1.3 times 10 to the 47th power ergs per second, more luminous than 1,000 quasars. Growing a black hole beyond this mass through Eddington-limited accretion requires an enormous supply of gas over an enormous time, and the self-regulation of accretion through AGN feedback may prevent the accumulation of sufficient gas in any single galaxy to grow beyond certain mass thresholds. The most massive known black holes, TON 618 at 66 billion solar masses, HOME 15, A-star at approximately 40 billion solar masses, are found in specific environments. the brightest cluster galaxies, BCGs, at the centers of rich galaxy clusters. These environments are unique because the BGC sits at the bottom of the cluster's gravitational potential, can accrete gas cooling from the hot intracluster medium and is subject to repeated galaxy mergers as cluster members fall toward the center. Each major merger brings additional stellar mass and potentially additional gas, growing both the galaxy and its central black hole. Ultramassive black holes are the product of the most extreme environment-driven growth in the most massive structures in the universe. The stellar core deficit observed around ultramassive black holes, the region of lower than expected stellar density at the center of their host galaxies, is a signature of growth through dry mergers, in which two galaxies with minimal gas merge, and the binary black hole at the merger product's center scatters stars out of the central region through gravitational slingshot interactions. The binary black hole eventually merges through gravitational wave emission, and the resulting single black hole carries the imprint of the previous binary in the form of a depleted stellar core. The size of the core deficit is proportional to the mass of the binary, providing an indirect measurement of the total mass of black holes that have merged to form the current ultramassive black hole. The question of whether there is a physical upper limit to black hole mass, whether some process prevents indefinite growth, is not resolved. Eddington limited accretion provides a growth rate limit, but not an absolute mass limit. Gravitational wave recoil during black hole mergers can kick the merged black hole out of the galaxy center entirely if the mass ratio and spins of the merging pair are appropriate, potentially halting the accumulation of mass. But the most massive known black holes appear to have remained at their galactic centers, suggesting that these kick velocities have not exceeded the escape velocities of their host clusters. Conclusion. So here is the complete taxonomy of black holes as we understand it in 2024. By mathematical type, the universe offers 4 possibilities, all derived from the no-hair theorem, the non-rotating, uncharged Schwarzschild black hole, the rotating, uncharged Kerr black hole, the most physically realistic description of the black holes that actually exist in the universe, the non-rotating, charged Reissner-Nordström black hole, and the rotating, charged Kerr-Newman black hole, the most general classical case, which unifies all 3 parameters into a single framework. These 4 mathematical types are the complete set in classical general relativity combined with classical electromagnetism. Every black hole that has ever formed, or that the universe could produce, falls somewhere in this 3-dimensional parameter space. By mass and formation mechanism, the taxonomy is richer. Stellar mass black holes, the most numerous, formed from collapsing massive stars and merging neutron stars, detected in their millions through X-ray binaries and gravitational wave observations, massing from 3 to roughly 100. Solar masses forming the basic population from which larger black holes can grow. Intermediate mass black holes, the elusive middle category, from 100 to 100,000 solar masses, with strong evidence from gravitational wave events and luminous X-ray sources, but awaiting the definitive low-mass confirmation. Supermassive black holes, the architects of galaxy evolution, millions to billions of solar masses, sitting at the center of virtually every large galaxy, detected through stellar orbits, AGN activity, and direct imaging. ultramassive black holes, the extreme products of the most massive environments, tens of billions of solar masses, found in the brightest cluster galaxies, carrying in their stellar cores the history of every merger that built them. Direct collapse black holes. The hypothesized massive seeds of the earliest supermassive black holes, forming directly from collapsing primordial gas without the stellar intermediate step, increasingly supported by JWST observations of the high redshift universe. Primordial black holes, the earliest possible category, formed in the first second of cosmic time from density fluctuations in the primordial plasma, spanning an extraordinary range of masses, evaporating at the low end and potentially constituting dark matter at specific mass windows. Micro black holes, the smallest possible category at the Planck scale or in the TeV range under extra dimension models, not yet detected and possibly never detectable, but theoretically significant as the objects at which quantum gravity and black hole physics meet. Beyond the physically realized types, the theoretical taxonomy adds white holes, the mathematical time reverse of black holes, almost certainly not physically present, but important as the structure revealed by the maximal extension of black hole spacetimes. Regular black holes, singularity-free solutions motivated by quantum gravity, and exotic mimickers, fuzzballs, gravastars, and other compact objects that reproduce the external appearance of black holes without their classical interior structure. What unites all of these is the same fundamental physics, a region of space-time so warped by the concentration of mass energy that the causal structure of time itself is redirected toward the interior. The specific manner of that warping, the spin, the charge, the mass, the formation history, determines which type of black hole you have. But the core feature, the irreversible redirection of time, the event horizon as a one-way door in the fabric of space-time, is the same across every type, every mass, every mathematical variant. There is one thing all known types of black holes have in common beyond their physics. They are windows. Windows into the most extreme physics the universe contains. Windows into the intersection of general relativity and quantum mechanics, where our two best theories of nature are simultaneously most relevant and most incompatible. Windows into the history of the universe, its first second in the case of primordial black holes, its first billion years in the case of direct collapse seeds, its entire 13.8 billion year history in the case of the supermassive black holes that have grown continuously since the cosmic dawn. We have imaged the shadows of two of them. We have detected the gravitational waves of hundreds of them merging. We have tracked the orbits of stars around one of them for 30 years. We know they exist, in their multitudes, throughout every galaxy we can observe. What we do not know, what the singularity at the center of each one represents, what quantum gravity does to it, where the information goes, what the fuzz at the Planck scale looks like, is what the next century of physics is for.